So, today is our 7th lecture in this course, starting with the introductory lecture, and this is the 6th lecture on fluid dynamics. So, if you remember last time we are talking about the macroscopic mass, momentum and energy balance, and I have also shown you some of the applications of the macroscopic models in the context of drainage through a tundish nozzle or emptying of a ladle and so on and so forth. So, having discussed the laminar flow, Navier-Stokes equation, the macroscopic equations, of course, in a very compact way, now is the time to talk about turbulent flows as well as some of the industrial flows, and those industrial flows particularly of concern to we metallurgists, we will see they are necessarily turbulent. Now, so far as I have classified flows on the basis of compressible flows versus incompressible flows, steady flows versus unsteady flows, one dimensional flow versus multidimensional flows, and there is another classification that comes and which I have just said so far, the distinction between laminar and turbulent flow, that laminar flows are basically low Reynolds number flow, and Reynolds number, if you remember, and this is the characteristic length, and then you have, and this is the kinematic viscosity in the denominator. Inertial to the viscous force, I have also said very briefly about the dimensional numbers which are of importance to fluid dynamics. And this Reynolds number characterizes whether the flow is laminar or a flow is turbulent, and turbulent flows are invariably characterized by a very large Reynolds number, and very large means even 100 Reynolds number can make the flow turbulent. And if you remember the creeping flow around a sphere which I talked about in the context of Stokes law, and there I was talking about Reynolds number of the order of 0.1 or so. Or less than 0.1. So, in such context, when the Reynolds number is 1 or less than 1, we will see that the viscous forces are as important or more important than the inertial forces, and then the flow really becomes laminar. But in contrast, if you get a value of 1000 or 10 to the power 4 or 10 to the power 6, which essentially means that viscous force is nothing in comparison to the inertial forces, and that is the time when we see turbulent flows. Now, what are the general characteristics of turbulent flows? The turbulent flows are basically fluctuating flows. So, if the flow is laminar, and if you put a probe inside, suppose this is a velocity and this is an instantaneous velocity, okay? And now, if I say that I want to plot as a function of time, so I have a reactor, I have put a probe inside a certain point or located or targeted at a certain point, and suppose the system is under steady state condition, that means the velocity is not changing as a function of time. So, if it is a steady flow and if it is a laminar flow, then the characteristic response curve that my equipment is going to register or the sensor is going to register will be a horizontal line parallel to the x axis as a function of time. On the other hand, if the very flow would have been turbulent, in that case what we would have noticed is high fluctuation superimposed on a mean line itself. So, turbulence basically are fluctuating flows. So, you can see that sometimes the velocity is above the mean line, sometimes it is down. So, it is fluctuating around the mean line. So, these are characteristics of a steady turbulent flow, and you see that these fluctuations have a frequency, and if we are talking about low turbulence, then the frequency could be something around 10 to 100 hertz, okay? And if it is a very strong turbulence, in that case we can have something like 1000 or 1 kilohertz frequency even. Now, the characteristics of turbulence, it is said that it is basically in chaos, but chaos always need not be turbulent. So, and the turbulent, how it originates in a system is that it necessitates some shearing actions. So, if you have no valve, for example, if there are smooth flow, in that case you may not see that a turbulent flow even at a very large Reynolds number. So, when you have a pipe flow at a very low Reynolds number, if you remember, if the pipe flow we assume it to be laminar flow and fully developed flow, then what we encounter is a parabolic velocity profile, and this I have at least made half the deductions in the class where I have not explicitly shown the Hagen-Poiseuille equation, but I have shown that if the flow is pressure driven, in that case if the flow is fully developed, if you simplify the Navier-Stokes equation, then you do get a parabolic velocity profile that I have demonstrated in the class. The same velocity profile, when it is turbulent, will get drastically changed and it will look something like this. That is the characteristics of it. So, the lower one is the turbulent flow and the upper one is the laminar flow. This is turbulent flow and this is laminar flow. So, this is the low Reynolds number flow and this is the high Reynolds number flow. And as I have said that to initiate these disturbances, so you start with a low Reynolds number and then you increase the Reynolds number, and at a certain stage you will see that the disturbances have originated in the system. So, typically if you look at the flow, then the flows are typically at low Reynolds number, they are, so these are walls and these are streamlines. That means, if I drop an ink into the flowing stream of fluid, okay, you will see that the fluid is following a certain path. It is neither fluctuating this way nor it is not neither moving this way nor moving that way. Suppose if it is in a fully developed region. Okay. So, it has a streamline pattern along which the dye is going to move without showing any fluctuations. But the moment the Reynolds number increases and you put a dye here, then what happens? You will see that the downstream fluctuation, the dye will start to spread in the system, and that shows that the flow has really become turbulent. So, the disturbances may be the Reynolds number itself, or maybe the friction at the wall, maybe there is a bluff object, or additional reasons. So, some kind of disturbances has to be precipitated. So, if you say that you just increase the Reynolds number, then the next stage what you are going to see, stage 2, is, I should write a little bit lower. So, you can see that the streamlines will be there, but somewhere a disturbance will set in. So, this is the disturbance I am talking about that will set in when you increase the Reynolds number, and there what is going to happen, the flow separation is going to take place if we increase. So, this is stage 1, you can see clear cut streamlines. In the stage 2, you can see that the disturbance has precipitated into some kinds of local velocities here, and then in the third stage what you can see basically is something like this. So, you have a strong rotational motion, and these are the streamlines. And there are, as I have said, that this sort of a features at high Reynolds number gets amplified and gets generated, and to generate them there could be various reasons. One important reason in this case is, as you can see, there are walls here. So, we are going to get or experience shearing flows, and as I have said, shearing flow is a necessary cause in order to introduce turbulence into the system. If you have a diverging flows, for example, that also can precipitate into a turbulent flow or such kind of rotational systems. Now, also if you have bluff objects, solid objects, in that case what happens, fluid grows and strikes and this flow separation takes place, and that also can generate turbulence. So, shearing flows, the walls, bluff objects, diverging geometries, these are all features which really precipitate into the formation of these rotational disturbances, which is shown here, and then ultimately what happens is you have pockets of fluid, and at many places you will see that there are discrete rotating components. So, there is a mean direction of the flow. So, these rotating components, they have their rotation and they are advancing along with the flow, but they themselves have a rotational component, and these elements we are saying that these are the eddying, or these are eddies in a turbulent flow, and these eddies are moving along with the mean path of the flow. So, the eddies have rotational components. So, therefore, we say that when you have turbulent phenomena, there is nothing like a one-dimensional turbulent flow. Turbulent flows could be a multi-dimensional feature. Turbulent flow could be basically fundamentally an unsteady feature, because there is going to be an velocity fluctuation in the instantaneous velocity all the time. So, this equation, as you all know, is equal to Vz. If z is this particular direction, then Vz is equal to Vz max into 1 by r square, where capital R denotes the radius of the vessel. And in this particular case, the velocity profile is substantially changed, and it is equal to Vz max, and that is equal to 1 minus r divided by capital R raised to the power 1/7. So, most of the time what we are going to see, we are going to see that a turbulent flow which is going to be essentially unsteady, which is going to be essentially multidimensional, which is essentially going to have large Reynolds number also. Now, this rotating components which we have said eddies, so these eddies move, as I have said, along with the direction of the motion. The eddies will exhibit random three-dimensional motions where a rotational characteristics is an inherent characteristic of turbulent flow itself. Now, if we plot the inverse of eddy size, we must understand that the local Reynolds number is going to be much smaller here, close to the wall, but the local Reynolds number are going to be very large at the center, because the local Reynolds number is going to be small here, because the simple fact that the velocity is 0. If velocity is 0, so at the wall, what is going to happen is that the Reynolds number is basically equal to 0, and as you go away from the wall, Reynolds number progressively, or local Reynolds number progressively increases. And as a result of which, what happens is you get bigger size eddies here, and as you go towards the wall, then ultimately what happens is you have a smaller size, because smaller size means what? You have a Reynolds number, if you remember, the Reynolds number, if you look at the local Reynolds number, then I can say that this velocity, okay, the length scale, if you look at the Reynolds number of the eddies, the eddying size has to be small, and then what happens is the velocities themselves are small, and then we have a viscosity here. So that means what happens is towards the wall, it becomes basically essentially a viscous flow. So in that context, around a solid surface, we can, as I have indicated, that the flow can go something like this, and there is a concept of a boundary layer. Okay? And this boundary layer, if this is the solid, in that case what happens is we can have fully turbulent regime is here. So this is the other end. So this is the solid wall, and then this is how the velocity varies as a function of distance, and this is distance, say x, and I will say this is v versus x profile. So therefore, this velocity essentially is a 0 velocity. If this is the scale of the velocity, this is v is equal to 0, and then this becomes is equal to v is equal to v infinity, or the free streams. And this sort of a variation gives rise to what is known as the velocity boundary layer. Okay? And in that boundary layer, we can have two different regions, or it can be separated into three different regions. One we call as a laminar sub layer. Why laminar? Because here there is no turbulent flow, because here we have velocity to be approximately is equal to 0. So the Reynolds number is approaching 0, and if you have immediately after the laminar sub layer, you can have a buffer layer where the flow may be partly turbulent, partly laminar, because where we have moderately high viscous force, but not entirely high to dampen the inertial effect, etc. And then we go to the bulk, which is the main turbulent flow of the system. Now, if we look at the eddy size distribution, so we will have eddies here also, eddies here also, eddies here also. So we will say bigger eddies here, because the simple fact that the velocities are going to be larger, okay, and as a result of which the length scale is going to be larger. So here we will have these eddies will be containing most of the energies, and if we plot this eddy energy, and then we get a graph like this, and this is of inverse of eddy size, which essentially means this is small eddy or smallest eddy, and this is large eddy. And there, this part is called the universal eddy size These large eddies will depend on, they contain the maximum amount of energy, okay, and their size will depend on what kind of a flow it is. Is it flow between two pipes, parallel plates, or it is flow between, a tank where we have a free surface and, 5 different walls and, 2 on the side, this side, 2 on the front and back, and 1 at the bottom. So 5 different walls on the free surface. This is one geometry. So we will have one sort of size of eddies there. So this we do not call, these are problem dependent, these are system dependent, these are geometry dependent, and these big eddies, their size is determined by the main characteristics of the flow, and they contain the most of the energies. But then if you go away from this main energy containing eddies, you enter an universal eddy size spectrum, which is characteristics of most of the shearing flows, and there you find that this is the size that we are talking about, through which actually energies pass from bigger to smaller eddies, smaller to smaller eddies, smaller to smallest eddies, and then ultimately it manifests in the lower gate thermal energy through the phenomena which we call as viscous dissipation. Viscous dissipation is negligible in the core of the flow. On the other hand, viscous dissipation is going to be more and more pronounced as you go towards the wall, and that is going to dampen the flow, bring it to 0, where the Reynolds number will become 0 and turbulence is going to be non-sustainable. Now, most of the industrial flows that we are going to experience are going to be turbulent in nature because of the simple fact that we have high Reynolds number of the flows. And also, as I have said, the turbulent flows are unsteady flows basically, and turbulent flows are multidimensional flows. So we have in the industry or in metals processing unit, we will have mostly unsteady multidimensional turbulent flows. So that is going to be the characteristics of the flows that we are going to encounter, be it the flow of molten steel in a ladle, be it the flow of an electrolyte in an aluminum Hall-Héroult cell. All these flows are going to be essentially turbulent because of the simple fact that our viscosity of the kinematic viscosities are extremely small for metal, and on the other hand the size of the industrial reactor is pretty large. So that the characteristic length scale is large, and that the kinematic viscosity of the fluid is low, and that makes the Reynolds number of the flow very, very high. So therefore we will see that in industrial reactors we will mostly encounter high Reynolds number flow or turbulent flow, and because our systems are bounded by walls and free surfaces, we are going to see that the flows are going to be mostly multidimensional flows. There will not be a predominant direction of the motion. Okay? So within the container itself, the fluid will be recirculating, for example, because the fluid cannot go out of the container. And of course, the flow can be turbulent, flow can be unsteady also, because unsteadiness is a characteristics. But there is, a formalism to deal with the steady turbulent flow also, but steady turbulent flow does not necessarily mean that there is no fluctuation. So it is, it's a representation of a fluctuating flow with a, some sort of a time averaging framework, so that you can extract some meaningful information on the mean flow. You may not get exactly the fluctuating flows, but you can really get this average of the fluctuating flows that determines or that characterizes the turbulent flow itself. One more thing is I want to introduce is a parabolic flow versus recirculating flow. In industrial flow context, parabolic versus recirculating flow. In a layman's terminology, the parabolic flows essentially tells us that there is a predominant direction of motion of them. So a pipe flow, for example, okay, through the pipe the fluid is flowing from, say along the x direction, on the ground. So it is moving from, say, from this side to this side. So there is a predominant direction of motion. There may be small motion on the transverse direction, but on the other hand, if you take, in comparison to this pipe flow problem, if you take the flow in a vessel, for example, in a cylindrical shaped vessel which contains molten metal, and then you find that suppose when you put molten metal or pour molten metal into the same, for example, this is the same scenario as you would observe in your bathroom, for example, when you open the tap just over the bucket. Okay? So then what happens is the fluid in the bucket gradually builds up, and the flow in the bucket is a churning motion. There is no predominant motion like what I have shown in the context of the pipe flow problem, where there is a predominant direction of fluid flow. Okay, this is the predominant direction of fluid flow, and that's how the flow is taking place. So this feature of a predominant one directional flow is going to be absent in the case of when you will be pouring molten metal into the vessel itself. And when you pour molten metal, typically the meniscus will, from lower level, it will gradually go up because you are filling it. It's an unsteady state phenomena, and then you have basically a flow which is going in this particular direction. So it's a clockwise moving vortex here, an anti-clockwise moving vortex here. So that is how the rotation really takes place. You can observe yourself. You can just open a tap next time you go to your bathroom, and if you have a bucket, and do this experiment to see yourself that you do not have a predominant direction of motion, but the flow of fluid is in different directions. So the tap opens, the stream of water goes down, it spreads at the floor or the bottom of the bucket, and then it goes up from all sides of the bucket itself. So this kind of a flow, where we do not see any predominant direction of motion, but it has a multidimensional flow characteristics, and that's basically is called a recirculating flow. So parabolic flows are those where we have a predominant direction of motion. Recirculating flows are those where there is no predominant direction motion. So we will say that our industrial flows, that the industrial flows we are going to generate, for example, in the case of an aircraft moving high up, you could see that the flow could be over the aircraft unidimensional in nature, because the aircraft is maintaining at a steady height and it is moving along a particular direction. There is a predominant direction of the motion. On the other hand, in metal processing unit, that sort of a feature, as I have just now mentioned, is not going to be seen. There are very limited number of scenarios where one can see, for example, a flow of this kind of. And I would say one example is when you drain molten steel from a ladle, through a ladle shroud into a tun dish, so through the ladle shroud, which looks something like this. So it is like a pipe. So the ladle is there, and then you have a shroud attached, which is a ceramic tube basically, and then you drain molten metal into another vessel. Okay? So the flow through this is akin to what I have shown here. So the flow here is predominantly, but within the tun dish itself, the flow may be multidimensional. Ladle, this is ladle, this is tun dish, and this is shroud, which is a ceramic pipe, and here the flow could be basically one-dimensional. But these are very special kind of a scenario. In general, the flows that we are going to encounter in metal processing industries or liquid metal processing industries are going to be mostly recirculating in nature. So the industrial flows are going to be essentially turbulent, they are going to be multidimensional, they are going to be characteristically unsteady, and finally, as I have indicated, that they could be recirculating or mostly recirculating. Compressible flows also we can generate, particularly if you go to LD converter, where you have supersonic oxygen jets. Okay? In that particular case, what happens when you get Mach number is equal to 1, in that case the compressibility effect comes into the picture, and in that case the assumptions that we have made so far that the flows are incompressible in nature, those are not going to be applicable. Now, having said so, let us also understand that the Navier-Stokes equation that I have written in its exact form, if you remember, I have retained the unsteady term, I had the 3 first order derivative term on the left hand side, I had the 3 second order derivative term on the right hand side. So I did not make any assumption whatsoever, and the equations that I have presented was the exact derivation. In deriving those equations, no assumption was made that whether the flow is laminar or flow is turbulent. Okay? So therefore, the Navier-Stokes equation as presented to you could be equally applicable to analyze laminar flow as well as to turbulent flows. Now, but there is a problem in trying to analyze the turbulent flow with the Navier-Stokes equation that I am going to discuss right now. Now, the equations that I have written, okay, as I have mentioned just now, are at least the flow characteristic assumptions I have not made. that the flow is either laminar or turbulent. So, which essentially implies that we can apply these equations to laminar as well as turbulent flows. But if you look at the equations, these equations are, if you have x direction momentum balance, y direction momentum balance, z direction momentum balance, continuity equation, 4 equations, 4 unknowns, they are non-homogeneous partial differential equations, they are non-linear equations. So, they will basically not be amenable to analytical solution. This is what is the analytical solution, which comes out by simplifying the Navier-Stokes equation, making that fully developed flow assumptions, constant property, steady state, and all these assumptions, and then we could derive this by working it out with hand. But when you apply the Navier-Stokes equation in its entire form, because we have to apply an entire form, because no simplification is possible. It is unsteady state, it is multidimensional, okay? It's high Reynolds number, it is turbulent. So, therefore, no simplifications are going to be available here, and in that case we can say that we have to deal with the exact form of the Navier-Stokes equation. So, that poses a problem that we will not be able to solve these equations by hand. So, we will have to have computational methods. We have to write computer program in order to solve those equations. Now, there are many solvers which are available. Or we call them as commercial softwares, which are available to solve the Navier-Stokes equation. So, you just define the geometry, define the boundary conditions, and the 3 equations are going to be, or the 4 equations, that is the equations of motion and equations of continuity, they are going to be applied. So, a numerical procedure, so we have a differential equation, we say partial differential equation, we apply numerical method, then you get algebraic equations. And these algebraic equations are actually solved by the solvers, which we call as a commercial softwares. Many of you will have a chance to use this commercial software during your tenure at IIT Kanpur. One such software that we have is the Fluent in the ANSYS. The other is also we have, I think, is a COMSOL software, which allows you, they are Navier-Stokes solver basically, okay? And you can have many permutations and combinations. You can solve 3-dimensional problem, you can solve steady problem, you can solve unsteady problem. Your job is only to define the geometry and lay the numerical grids. Now, so what is the task of a numerical method? The numerical method is applied to transform a partial differential equation or an ordinary differential equation into its corresponding algebraic equation. Okay? So, therefore, in order to know these solvers or do something tangible through these solvers, you have to know the numerical methods also. So, this is an entirely different subject actually now we will get into, that if you want to solve the Navier-Stokes equation which you have derived in this class for actual industrial flow, in that case, you cannot do it by hand, you have to write a computer program. Writing a computer program takes an enormous amount of time. So, you take recourse to industrial solvers or commercial softwares, and these commercial softwares will be allowing you or giving you a platform to solve those Navier-Stokes equations which are applicable to your system. So, as I mentioned that partial differential equations are transformed into numerical methods, and then then you get algebraic equations, and these algebraic equations are solved, okay, not in a continuous fashion, but on certain points which we call as grid points. So, we will in a 2-dimensional domain, a grid is going to be constructed, and then these are grid points I can say, or we can write like this also. So, these are the nodal points at which we will seek the solution of the algebraic equations. So, the domain discretization is done, a numerical grid is, because you will apply a numerical method, you got the algebraic equations, now you have to solve these algebraic equations. For every node you will get one algebraic equation. So, you will get many algebraic equations actually over the entire domain, and this you have to solve simultaneously. So, if you imagine a very large domain, you can have millions of such nodes and you can have millions of algebraic equations. So, therefore, you will require a powerful computer in order to solve this. Now, the moment you apply these numerical grids, what happens is that, if you remember, as I said, you have large eddies here, you have small eddies here. So, if the grid is not to find, then if you have the small eddy size, which is this, then this kind of a grid distribution will not be able to resolve the motion of the smallest size. Okay? So, therefore, it becomes a big problem to apply the Navier-Stokes equation as it is and try to simulate an actual industrial flow problem. And it arises because you will require very, very fine grid to resolve the motion across the length scale, small eddies, smallest eddy to small eddy to large eddy to largest eddy. Everything if you want to simulate, then in a huge domain like 3 meter, 5 meter by 5 meter, which is the size of a metals processing reactor, you will maybe, God knows, 10 million, 20 million nodes you will be. And if you have unsteady state flow, okay, small time step advancing, so possibly one calculation will take 1 month, 3 months, 5 months. And we have not been able to do for our full scale reactors, this kind of a simulation where we can resolve exactly the motion of all the length scale or motion across the length scale. So, this part, if you can resolve it, that procedure is called a direct numerical simulation. Direct numerical simulation means you have not made any assumption in the solution of the Navier-Stokes equation. You have applied a computer program, but by solving the equations across the length scale, you have been able to predict the motion, or you have been able to calculate the velocity fields. Okay? And this direct, so please note it, it is DNS, direct numerical simulation. Okay? It is exact simulation of the turbulent flows, but it is very expensive, time consuming for actual industrial flows. So, therefore, we really do not do it for every analysis of every problem. So, we resort to a mechanism which we call as a time averaging of flows. So, we will time average, and then by time averaging we will solve the Navier-Stokes equation. So, we will have now, we have a Navier-Stokes equation, now I will say that we have a time averaged Navier-Stokes equation. I will just brief the time averaged Navier-Stokes equation. This approach is also called in the numerical world as RANS, Reynolds Average Navier-Stokes Equations. Reynolds Average Navier-Stokes Equations. So, the moment I will time average, I will also have a time average equation of continuity, time average equation of x direction motion, time average equation of y direction motion, time average equation of z direction motion. So, I will still have 4 equations, but in their time average form, and those 4 equations as opposed to the original Navier-Stokes equation will be the time average Navier-Stokes equation, or in short RANS. Now, as I said that you have an instantaneous velocity, and this instantaneous velocity can be decomposed into a fluctuating velocity. Suppose it is an x direction velocity. So, that x direction velocity I would say is a x direction time average, and fluctuation is a fluctuation of the x direction velocity component. Similarly, we can have other components also, the x component, so we have y component, we will have z component. Now, the time averaging, basically this is done, if you do this, the definition is that is what it is. And we have to remember that the limit of integration is, because we are time averaging it. Okay? So, you can imagine that one is called space averaging, the other is called time averaging. Okay? And suppose if I say that you can find out time averaging in the context of if you want to do, for example, rainfall in a certain month. Okay? So, day 1 so much of rainfall, day 2 so much of, so what you are doing day 1, day 2, day 3, these are basically time frames. So, that number in the month of January or in the month of July you get this much of rainfall, it is actually a time averaging of many data collected over that particular month itself, and then you have one representative value. So, similarly here also you have an instantaneous velocity which is changing as a function of time, okay, and you want to do a time averaging, and here, so this is the period over which you are doing the time averaging. So, this could be January, this could be April, okay, and this could be rainfall, and this could be the time, and this is April minus January, which is 3 months. So, 1 by 3, then you get month average rainfall, and here you will not have the velocity, but a month average rainfall. So, that is basically the definition. One important characteristic here is the limit of integration must be higher than the fluctuations, frequency of fluctuations here, because I want to capture, if I have, for example, one fluctuation is like this, and I have a time span t and t0 here, then I am not capturing the fluctuation at all. Okay? So, the span of the time span of integration here, the time averaging, the span over which time averaging is done, that has to encompass a sufficiently large number of fluctuations. So, I would say a delta t, if I take a delta t value, differential time, or which is equal to t0 minus 0. So, that delta t must contain a large number of fluctuations, that we must, this time period must be larger than the time period of fluctuations of the turbulent flow. Now, if you do like this, then what you get here is, if you substitute it 1 over t0, and then we get u bar, okay, 0 to t0 dt, and then you get, plus 0 to t0 and then u bar. And then you can see that this is basically comes out to be the definition. This term u bar, as you can see in this figure, is not dependent on time, because this is a horizontal line, as you can see here. This is the time average part itself. So, this is not function of t. So, this can be taken out of the integral. So, I can say this is u bar, and then the integration of this is t0 divided by t0, and that is what. And this part is equal to 0. Why? Because there are positive fluctuations, there are negative fluctuations, and those fluctuations, some of them are going, all of them, if you sum them up, all positive and negative fluctuations are going to annihilate, and therefore, you are going to land up with the time averaging of this definition gives you that it is equal to u bar. So, it is based on this we should be able to derive a form of the Navier-Stokes equation. For example, if you look at, I will show it for one dimensional, even though turbulence is not a one dimensional phenomena. So, you can say that let us look at this. Let us look at this equation, which is the continuity equation, okay, and then these are instantaneous velocity now, because we are applying, this is, I will write it v, instantaneous, and then this is w instantaneous, and that is compressible, incompressible turbulent flows, and then we say it's a 3-dimensional scenario. So, we will, this is z, and this is w is the velocity component, this is x, which is, as I have written here, u is the component, and this is y, or I will write it y is, this is better, v, and then this is z. This is a better convention, writing the z-axis along the vertical direction, but anything can go, you can change it, there is absolutely no problem. So, this is, so this is the, now the Navier-Stokes equation. Only thing is that earlier when I wrote the Navier-Stokes equation first, I did not say anything about u. Now, I am saying let us interpret that u as the instantaneous velocity. If it is the laminar flow, then whether you write it ui, or whether you write it by u bar, or whether you write it as u, it does not make any difference. Okay? But by writing at ui, you essentially meaning that you are talking about instantaneous flow, and then you will have an understanding that because I am talking of instantaneous flow, maybe I am talking about turbulent flow. Now, if you split up this term into an average term and a fluctuating term, then and time average it, this exercise you should be able to do. Actually, you will land up with this equation. In which u bar, v bar and w bar are the time average components of the instantaneous velocity as I have defined here. Because the moment I write it into two parts, okay, let us do it like this. So, this is going to be this, we will have it u bar, and then we are going to have it. So, we forget about rho, we can take a rho out, okay, and then we can have u prime. Okay. And then once you do the time averaging operator, then we have rho and 1 by T 0, and then we say, look, this term is going to be time averaging, so 0 to T 0, and this is going to be u bar dt, and this is going to be T 0, and this is going to be u prime. This term, as I have indicated to you, already is equal to 0 because of the cancellation of the fluctuations, and this term will come out to be u will come out, and therefore, you are going to get essentially this term here, even though we have gotten this term, the contribution of this is going to be is equal to 0. So, it applies to this term also, it applies to this term also, no problem. So, if you take the continuity equation, overall mass continuity equation, and if you write them not as ui, not as vi, not as wi, but u bar, v bar and w bar, then you will interpret that you are talking about the runs, or the average, time average equations, or we can say that is a time average equation of mass continuity. Now, let us look at, I am going to finish this discussion today. I am a little behind the schedule. We should have started discussing the problems today, but now if you look at Navier-Stokes equation, for example, I take again one direction term, okay, or the terms along one particular direction. If you remember, and as I said, the moment I write the equations, you should be able to visualize yourself. So, let us talk about the Cartesian coordinate system. Let us look at the x component of the motion, and let us write down, let it be a multidimensional flow. Let us write down only the first order and the second order terms, okay, pertaining to the x direction equation of motion. So, along the x direction, if it is horizontal, we have an unsteady term, we have 3 convection terms is equal to pressure gradient term and 3 diffusion terms, and there is no component of the gravity. That is the general case of the x direction momentum balance equation. Of this, let us pick up just one first order term, because the treatment for all other remaining other two first order terms are going to be. So, this is what it is. We have rho u I into u I now. This is the first order fate of the first order term. Earlier it was rho u u, now it is instantaneous velocity, and then we have a corresponding on the right hand side we have to now time average it. So, I have just expressed it, now I need to time average this. Now, if we substitute in place of this, and if I substitute here, in place of this, the time averaging of this, as I have indicated, will yield you this term. Because u prime time average is going to come out to be 0, as I have indicated already. So, immediately the second order terms can all be interpreted not as u, not as u bar, but with a not as u ui instantaneous velocity, or not with u, just with a u bar. So, you can write the 3 second order terms on the right hand side with their corresponding bar. But what happens to this term? This term, when you multiply this, then what happens is that you have an unknown correlation which will surface. First term, both have time average values, time integration or time averaging is no problem. The second term, this multiplied by this will come out of the integral, time averaging of this will become equal to 0. So, from here you are going to get two different terms only. One is associated with this u mean into u mean, but the other is the time average of this particular component which we represent like this. This essentially means that it is that is this particular term with an over bar above it. Now, we have no mechanism to get this correlation, this velocity product, fluctuating velocity components. Okay? So, therefore, we will have, if you remember, we have 4 equations, 1 equation of continuity, 3 equations of motion. Similarly, we have u bar, v bar, w bar and p bar. So, 4 equations and 4 unknowns, clear cut. But the time averaging has produced us an additional term like fluctuating velocity squared. Where from do you get the information about the fluctuating velocity? So, these are unknown correlations which have appeared into the equation as a result of time averaging, and to get information on this, what we do? This is called a closure problem. Time averaging produces higher order correlations. Higher order means the second order terms, higher order correlations with fluctuating velocity components which are not known. So, 4 equations, 4 unknown is set. This is the additional unknown. So, somebody has to give me that. Only then I can have, look, I have 4 equations and 4 unknown because sir has supplied me this correlation. So, who will supply this correlation? These correlations come from what we say as a turbulence models. This is a very big subject, I do not want to get into it. So, time averaging produces unknown correlations which are not known. So, then comes my equations are not closed because I have more unknowns than the number of equations. So, I have to close this problem, I have to bring it to the form that when I have as many equations as unknowns. So, I will apply a turbulence model, and this turbulence model is going to be giving us information about these fluctuating velocity components. Now, if you look at these terms rho, u bar, v bar, time average, this has the term of, this is called Reynolds, this has the, if you multiply, these are basically stress terms, velocity multiplied by the product of the fluctuating velocity components, and these are product of the same velocity components, these are different velocity components. This gives us what is known as a turbulent shear stress, this gives us as a turbulent normal stresses. Okay? They have the dimension of stress or momentum flux that they are associated with fluctuating velocity components. We call them as not laminar shear stress or molecular shear stress, but we call them as turbulent shear stress. So, how do you estimate this turbulent shear stress? Various, there will be different components of course, because you have u, v and w is a subject that we do not talk in this course, and that you can assume that that is known as turbulence model. So, therefore, if you apply, to summarize, I would say if you apply the time average form of the Navier-Stokes equation, you will have to apply a turbulence model to close the set of equations. There are a good number of choices available. So, you can pick up one of those turbulence model, and the turbulence model together with the Run's equations will give you a complete framework for analysis of turbulent flows in industrial reactors. There is, from this point onwards, one can go into the details of turbulence model, but I do not want to talk, there is no scope to discuss such things in this particular course, but it is sufficient for us to know that the exact laminar flow equation, exact equations of Navier-Stokes equations that we have derived are equally applicable to turbulent and laminar flows. But applying them to real life turbulent flows create a problem, because we want to resolve all the motions, and we want to therefore have very fine number of very fine grids that will increase the calculations, because we will have 10 million equations, 20 million equations, and as a result of which it does not become practical still today. So, we want to find out an alternative way of how to address a turbulent flow, and one such approach that only I have discussed here is called most popular and common approach that we use in metallurgical engineering is the Reynolds approach or the time average. And as I said, if you want to apply the time average Navier-Stokes equation and continuity equation, you have to have a turbulence model, and that turbulence model, I think it is sufficient for you to know the turbulence model is needed to close the set of equations to have prescription or values of the Reynolds stresses. And how do you get this exact equation, way of deriving the turbulence models, or what are these turbulence models, that we do not discuss. So, I think the discussion about turbulent flows and industrial flows are over. So, that means whatever I was supposed to cover in the bit of the 6-7 lectures that I have covered, in the next class we are going to solve some problems, and those problems are of course going to be all simplified problems, because as I said that solution of the exact Navier-Stokes equation is not possible. You have to go to the computer center, use software, etc. So, we will solve those equations in their simplified forms, steady state, fully developed flow, constant property flow, so on and so forth. Few examples I will work out. I will also give you the sheet of assignments, and you will have solved those equations and then get certain expertise, or some expertise at least, in tackling the problems as well as solving them, getting some useful information out, and in the process getting the necessary fundamental knowledge. So, we will continue.